All right. Good morning, everybody. I hope you enjoyed the dinner yesterday and recharged for today's lectures. So we are very happy to have Stefano Forte from the University of Milan, who is a world-renowned expert in QCD and in particular in extraction of collinear structure from XML data. He will give a set of collinear structure.
Okay, thanks. Thank you very much, Alexei. Thanks to Fred and Alexei for inviting me to lecture here. Unfortunately, I missed the dinner yesterday night, but I'll do my best to entertain you nevertheless. So I've been asked to talk about collinear structure. So I suppose after you've heard wonderful things, including from Alexei about 3D structure of the nucleon, I should start telling you why collinear structure is interesting. And the key to that is if you look at these plots where I stuck on top of each other, the plan of what's happening right now at CERN, at the LHC, and what will be happening and what's happening as far as the EIC is concerned. This is an EIC school. And one thing that strikes anyone who looks at these plots is that, right now, so for example, at CERN right now, 2023, 2024, we are approaching the end of some LHC run at the highest energy that has been reached so far. And then pretty soon there will be what is called LS, which stands for long shutdown 3, which is in preparation. You see HLLHC installation of the high Lumi LHC, which is, according to many people, something that you should really think of as a new accelerator, because even though the energy is just marginally higher, it's 14 TeV instead of 13.6, the detectors are going to be completely redone, and the luminosity of the beam, the magnets will change. And so the whole physics program will be very much geared towards trying to find finally some evidence of new physics, possibly dark matter, in very precise measurements. So, the LHC has already turned Hadron Collider physics into precision physics, and this will bring that to the extreme. And then you stick it on top of the EIC, and you see that, there we are sitting 2024, 25, conclusion of RIC operations, which is almost simultaneous to the conclusion of CERN round 3, and then you have the construction phase for the EIC. So it's really parallel. And by the year 2030 something, 21, 31, 32, both the high Lumi LHC and the electron ion collider should be producing physics. And there is obvious synergy between the two, and this synergy goes through collinear structure. And the reason is in this slide or this plot. So what I'm showing you here is a breakdown of the uncertainty on the production of Higgs bosons. So this is a plot that was produced by the Higgs cross-section working group a few years ago, and it was kind of updated in these comments here by Raoul Runch, who gave the summary talk on precision Higgs physics at the Lesouche meeting a little less than 1 year ago. And basically the message is that you have a breakdown of uncertainty where most of these uncertainties are gone. So for example, there was one uncertainty having to do with 1/n top corrections that have now been computed, so this has gone. There was some uncertainty due to the contribution of heavier quarks, that's also gone. Something having to do with mixed QCD electroweak corrections, that's also done. Something having to do with the fact that only next leading order PDFs were available, while this calculation was next cube leading order, that's also gone, because during the last several months, next cube leading order PDFs are left. And in the end, the only uncertainty which is left is the big blue band up here, which is called delta PDF and alpha S, which is the uncertainty on the knowledge of the collinear structure of the nucleon. So knowledge of the collinear structure is going to be the main bottleneck at the high Lumi LHC. And obviously the electron ion collider is the prime place where in deep inelastic scattering, which is a very clean setting, one will be able to extract in a completely unambiguous way collinear structure, and then through the magic of factorization that you've been hearing about from George Sturman in the last several days, one takes, the nucleon structure is universal, so you take it from electron-proton collision and you bring it to proton-proton collisions, and hopefully you compress down this uncertainty. So, the reason for being interested in collinear structure is twofold. On the one hand, we are interested in the structure of the proton, and obviously 3D structure is richer, but collinear structure is more precise and accurate. So we have the possibility of understanding something about the proton or the nucleon, which is perhaps a little less detailed than in, say, TMDs or GPDs, but is much more precise and accurate. And also it's on a very solid theoretical footing. But then there is also the aspect that we are gaining knowledge of a tool that will be crucial in doing physics at the energy or luminosity frontier, so in doing discovery physics. So this is my motivation. Now, you've been hearing from George about factorization, and George is of course one of the grand masters, one of the fathers of QCD factorization. So you heard from the horse's mouth how factorization works and where it comes from. In my two lectures, I'm going to take a very kind of down-to-earth approach, and I'm going to try and answer some very basic questions. So, for example, how does factorization relate physical observable to PDFs? Maybe at a very naive level. How is the kinematics of what you measure in an experiment related to the kinematics of the PDF that you're measuring? And how do PDFs look like? And people. So here, when I say PDFs in these lectures, I always mean collinear PDFs, the one that depend on only one scaling variable, and then on one scale. Okay, so how do they look like? Probably roughly, but why can we understand that? And then how is the prediction for something that you measure in an experiment affected by the shape of PDFs and which PDFs enter the prediction? And turning this around, how can you use measurements, experimental measurements, to determine PDFs? And then, I told you how important understanding PDF uncertainty is. So what are PDF uncertainties? Where do they come from? Can we control them? How do we determine them? So as I said, I'm going to take a very, very down-to-earth approach. I'm going to try and ask very naive questions, things that you may think are kind of trivial, but then maybe one is slightly confused about, and maybe I'm confused. Was confused about them, and then I'm going to try and tell you some tricks. I mean, most of the little bits and pieces of understanding that I'm going to be talking about are well known and obvious. A couple are maybe a little less well known, but you know how it is. When you work in one field, there is a lot of knowledge which is passed on based on oral tradition, and you don't read it in books somehow. So I'm going to try and tell you a few of these things, and hopefully answering naive questions will allow you to raise and think about deep questions, which I leave to you. Maybe at the end of the lecture, I have a slide with questions that you can use as food for thought. Okay, so one thing. So given the way I'm gonna cover the subject, I like that. My whole point is to try and understand some little details. So if you don't understand, please stop me. I mean, raise your hand, ask questions. I'll be very happy to stop. It doesn't matter if I don't cover. I prepared a bunch of slides, but whatever. I mean, I'd rather do something less, but have everything perfectly clear rather than go, rush through the slides. I'd be happy to work out something on the blackboard. So by all means, stop me during the lecture. Don't wait until the end. Remember, there are no stupid questions, only stupid answers. And also remember that if you have a doubt and you think there's something you didn't understand, most likely if you ask the question, half of the audience will be grateful because they have the same doubt. That means that I have not explained myself very clearly. So please do stop me and ask questions. Okay, so let me start with a basic reminder of how factorization works. I started emphasizing the parallel between lepton-hadron, EIC, and hadron-hadron, LHC. So how does factorization work in these two cases? I mean, of course, you heard the whole formalism and the derivation from George, but once you go and get and do the calculations, how do things actually work? So the way things work is that you calculate some partonic sub-process, which you calculate using Feynman diagrams, where, say, if you're doing DIS, you have an incoming photon and an incoming parton. Here it's drawn as if it were a quark, but it doesn't really matter, a parton. And then the whole kinematics is described at the macroscopic level in terms, if you're looking at the simplest case, so a totally inclusive cross-section, say structure function. I'm going to get to the details of that. Then you just have the scale, which is the virtuality of the photon which is coming in, and then you have the mass of the final state which are produced. And out of these two quantities, you construct a dimensionless ratio, which is pure kinetics. And these are things that you actually measure in the lab. However, these things which you measure in the lab are related to what you actually calculate in Feynman diagram by assuming, and that's the collinear structure, by assuming that the incoming parton carries a fixed fraction y of the momentum of its parent proton, so that they are parallel. And then this obviously relates the kinematics in the Feynman diagrams to what you actually measure in the lab. And then the whole process is factorized in the Feynman diagrams you computed times something that weighs the different values of the momentum fraction y, and this is what we call a collinear PDF. Okay, so this is the kind of basic idea. And if you go to hadron, well, there are a couple of things that change. I mean, the first thing that changes is that you have two hadrons in the initial state. So you have two incoming partons, each of which carries a fraction, xy or x2, of their parent hadron's momentum, P1 and P2. And then as macroscopic kinematic variables, you typically use the invariant mass of the final state. So if you're producing Higgs, the mass of the Higgs, say, and then again, like in this case, the total invariant mass of the final state, if you're looking at the cross-section. And in fact, you take then a scaling variable, which is sometimes called tau, or usually called tau, the ratio of the two. So the invariant mass of the object you produce, the Higgs mass, or here I wrote W mass, assuming you're doing W production, divided by the mass of the hadronic collision. And then by imposing that the or gluon momenta are proportional to the proton momenta, you relate again the macroscopic kinematics with the microscopic kinematics. So this is all said in words, but I want to look at it a little more quantitatively. However, before I do that, let me take a very first look at the weight that you're putting here to this little y, or the x1s and x2s, which is what we call PDFs. So I'm showing here, I'm going to get back to this plot later, but I'm showing here a first plot. This is a particular set of PDFs, but it doesn't really matter which set it is. But there are a few things that I'd like to start observing about this plot. So the first thing is that when you look at a plot like this, you should realize that what you're looking at is a set of correlated probability distributions of quasi-probability distributions. So let me explain this. So each of these curves, so for example, you take the gluon curve here, which by the way, notice is divided by 10. So the actual one would be up the scale of the plot. So this is telling you something which is the weight with which you weigh a gluon that carries a fraction x of the parent proton's momentum. So you can think, well, it's the probability of the gluon to carry a fraction x of the parent gluon of the parent proton momentum, but it's not quite a probability. That's why I called it a quasi-probability, because it could be negative. So you could have negative weights. So it's not quite a probability. But these curves also have a band, and the band is an uncertainty. These are functions. So what you're looking at is an uncertainty in a space of functions. And moreover, so it's a set of probability distributions in a space of functions where the functions are these quasi-probability distributions, and all of these uncertainties are actually correlated. So say how wide this band here is correlated to how wide this other band is there. And so this is a very big infinite dimensional object. So first, this was the first naive simple observation, which you should keep in mind, however. The second thing is when you look at a plot like this, notice that what is plotted here is not the PDF, but rather x times the PDF. And I mean, this is a plot which is always made, but sometimes you forget that this is x times the PDF, but it's plotted on a log scale with on the x-axis and the linear scale on the y-axis. So this means that the x here compensates for the log scale, so the area under the curve is a number. Okay, so say the area under this red curve here, which is the difference between the total number of up and up anti-up quarks, is the area is the total number of up minus anti-up quarks. The other thing is that indeed the typical plot which you look at, this you find on the PDG, for example, typically shows the up and down valence, where valence means quark minus anti-quark. So the area here is 2 net variant number of up quarks and 1 net invariant number of down quarks in a proton. And then what people plot typically is U bar, D bar, charm, and the gluon. And the first naive observation is that these guys grow at small x, meaning that it's very likely to have anti-quarks, or as people say, C quarks and anti-quarks and gluon that carry increasingly small momentum fractions of their parent hadron. Okay, so when you actually use these guys in factorization formulas, you end up with formulas that look like this one. So here I'm writing an equation, what previously I had in graphs or in words in the previous slide, 2 slides ago. And again, I'm doing a parallel between one hadron in the initial state and 2 hadrons in the initial state. So for the time, so I had first a very cartoonish picture with just the little diagrams. This is a little less of a cartoon because it's equations, but it's still a cartoon because I only have one so let's say one quark, which I'm calling Q, and one cross-section, and I'm going to get to greater detail in the next slides. So one hadron in the initial state, you have some physical observable, which I'm not writing the dependence on scale, so the virtuality of the photon. I'm writing only the dependence on one single dimensionless variable, which is the only thing you measure in the actual experiment, which is, in this case, X Bjerkane in DIS. If K is fixed, which is defined in terms of measurable physical things. So P is a proton momentum and Q is the gauge boson, the exchange photon or W or Z's momentum, which you can actually measure from the difference between the incoming and the outgoing electron momentum. So these are measurable quantities. So X Bjerkane is something you measure in the lab, and the way the macroscopic kinematics that you measure, so this X guy here is related to the microscopic kinematics, is by this delta function, which tells you that the cross-section which you calculate from Feynman diagrams, which is called S hat here, so it's what you calculate with incoming quarks and gluons, depends on a scaling variable, which has exactly the same shape as this one, except that the momentum P, which stands in the basement here, is Y times the momentum of the parent proton, and this then tells you that the two are related by this delta, and when you work out the delta, you end up with a convolution. And Q is the quasi-probability I was talking about, so the thing that weighs the integral over all the possible momenta, and obviously you have a minimum value because the incoming, say, quark must carry at least enough energy to produce the final state you observe. It could carry more energy, but it cannot carry less. So the minimum value is the value. So the momentum fraction that these guys carry is at least enough to produce the final state at threshold, right, with nothing else going on. Okay, and then you end up with a convolution, which is sometimes represented in this way. And the reason why it's represented in this way is that the convolution has a nice property of being symmetric. So you can decide whether you want to write it like the PDF, which is called Q here times the protonic cross-section, depending on the ratio, or the other way up. So it's completely symmetric. Okay, now when you go to 2 hadrons in the initial state, it works in the same way, except that now you have 2 PDFs. And so Q1 X1 and Q2 X2, because you have 2 hadrons, and then you have the 2 momentum fractions. And then it works in the same way. You have a macroscopic scaling variable, which is the mass of the Higgs, or the W, divided by the center of mass energy, which is, at the LHC, this is a 13 TeV. It's a collider energy, the energy of the 2 protons. So this tau is really the Higgs mass times the or the W mass, or when you do W production, you can do on-shell or off-shell W production. So it's an invariant mass of the decay products of the W's or Z divided by the collider energy. So it's something you measure, and this is related to the cross-section which you calculate with Feynman diagrams, which is called sigma hat, by imposing that the center of mass energy, which you have here in the basement at the partonic level, is obtained by multiplying P1 and P2 by their respective momentum fraction, X1 and X2, and weighing this with the Parton distributions. And then you work out the delta, which is just equating the momenta, and you end up with a double convolution. Now, the nice thing about the double convolution is that it's a double convolution because you have PDF1, PDF2, and the partonic cross-section. The double convolution is threefold permutation symmetric. You can turn it in many ways. The nicest way of writing it, which is what people usually do, is to write it as a convolution of the partonic cross-section. So it looks like exactly like in DIS, times something which is called the Parton luminosity. And the Parton luminosity, in turn, is the convolution of the 2 incoming PDFs. Okay, so the parton luminosity for the collider is the exact counterpart of the PDF in deep inelastic scattering. If you want to know what you're measuring in a hadronic collision, you go and look at the luminosity, and the luminosity is in turn obtained by folding two PDFs. But that's the way you relate the hadronic to the partonic kinematics. So the luminosity is a very important quantity because it's telling you, the basic partonic input to a hadronic process. So the luminosity stands to the cross-section at a hadron collider, like the PDF stands to the structure function at an electron-proton collider, like the electron-ion collider. Okay, so I said that this was less of a cartoon than my first slide, but it's still a bit of a cartoon for various reasons. I mean, first of all, this is a cartoon because here I'm just writing sigma of x, and second, because I'm just writing q of y. So this is an oversimplification because, first of all, you don't really measure a cross-section, or rather, you measure, so you don't really measure the basic underlying cross-section, you measure an electron-proton cross-section. The electron-proton cross-section, in turn, depends on the kinematics of the electron. So the kinematics of the electron, in turn, is related to the momentum of the gauge boson Q, which is a photon or a Z or a W, which is then what enters the basic underlying collision, which is what I was having in this slide here, right? So here there was no electron, and now I put the electron back. So this means that in an actual physical experiment, on top of the kinematics I already talked about, the gauge boson virtuality and Bjorken X, you also have the leptonic part of the kinematics. So you have a Y, which is the leptonic fractional energy loss, and then you have a center of mass energy of the lepton nucleon collision. Now, of course, if you're a theorist, usually you don't worry about it. If you're an experimentalist, you do worry about it. And in fact, in DIS, what experimentalists do is work out various clever ways of extracting from the kinematics of the measured electron-proton process the underlying kinematics of the virtual gauge boson hadron collision. So this was the first complication. So the quantity that factorizes, as in my previous slides, are these F3, F2, and F1s that I wrote here. So the cross-section is related to these guys by factors which depend on Y, and Y something which depends on the lepton kinematics. So the experimentalist will do the work for you and tell you, well, this is the structure function I measured, but don't forget that what is really measured is this guy here. So this was complication number one. Of course, this complication in turn entails that you have several form factors, each of which factorizes, each of which will have the structure. So each of these Fs, you see I wrote them as Fis, has the structure of a convolution of a partonic cross-section, which in DIS is usually written as C, or coefficient function. Coefficient function, partonic cross-section is the same thing, times a PDF. Okay? Here actually, well, I took the most general possible case, which is the case in which both the electron and the proton beam are polarized in general, in which case you have both spin average and spin differences of structure functions here. And then you have three unpolarized structure functions, which are spin average, three polarized structure functions. I'm talking about longitudinally polarized, so polarized along the direction of the beam. And each of them can be further classified into parity conserving and parity violating. The parity violating ones receive contribution when here you exchange a W or a Z, while the parity conserving ones receive a contribution when here you exchange a photon. Okay, so this was complication number two. And complication number three is that here you see in the factorization formula, now I have a sum over J with Cj and Fj, because really, when you do the factorization, it could be that the virtual gauge boson hits as an incoming parton a quark, an up quark, an up anti-quark, a gluon, whatever. So according to which partons enter the process, you have a different contribution here, meaning that you have a different C, a different partonic cross-section, and a different PDF there. Okay, so this is taking a closer look to DIS. Now let me take a closer look to a hadronic process. So let's say I'm doing Drell-Yan. By Drell-Yan, I mean W or Z production. If I was doing Higgs production, it would be just the same. So now there are two hadrons. I produce some W or Z that decays into a lepton-anti-lepton pair. So, if it was a W, it would be an electron and a neutrino, for example. And then what you actually measure in the most general case is a fully differential cross-section, which is parameterized by the kinematics of the lepton-anti-lepton pair. So by the vector Q, which is the 4 vector of the W or the Z, which in turn you can parameterize by its mass. I mean, it doesn't have to be on shell. If it's a photon, it's typically on shell. Zero. And even if it's a W or a Z, you typically do, high mass or low mass, meaning above or below the mass of the object. So there is an M square here. Then it's parameterized by a transverse momentum, which is in principle a 2 vector, which are the 2 components, though the azimuth is usually not very important because at an experiment like at a collider like the LHC, everything is azimuthally symmetric. So the angle is not so important, but the modulus of the transverse momentum, which is transverse with respect to the collision axis, which is called PT, which is called PT here, is important. And then you have the Z, whether the thing is moving to the left or to the right with respect to the center of mass of the collision, which is usually parameterized by what is called rapidity, which is simply the boost between the center of mass frame and the frame in which this guy is moving, in which this guy is at rest with respect to the z-axis, okay? So the fully differential cross-section will be differential in M square, PT modulus, though typically it's PT2 vector, though typically it's PT modulus because the azimuth is symmetric, it's just a 2 pi, and a rapidity dy. And then let me look at the typical things that you look at. So the first typical thing you look at is the rapidity distribution. So the rapidity distribution is the cross-section where you integrate with respect to transverse momentum, but then your differential with respect to invariant mass, which is what I was talking about previously, but also with respect to rapidity. So how much the W or Z, so not just the mass of the W or Z, virtual W or Z, but also whether it's boosted to the left or to the right. And this is called big Y. Now, in this case, factorization still works. So you still have a factorization formula with 2 PDFs. Now I've written it completely with the sum over all possible kinds of partons. So you have parton of kind A coming from hadron number 1, each of them with a momentum fraction x1 and x2. You have a partonic cross-section. The partonic cross-section, in turn, has its own rapidity. So you have a boost of the W with respect to the center of mass of the partonic collision. But the center of mass of the partonic collision, in general, is not the same as the center of mass of the hadronic collision, because if you have, say, that x1, so the fraction of the momentum of the parton which is coming from, my left to your right, so let's say this one is bigger than this one, then the whole thing will move to the right, because this guy is carrying more longitudinal momentum and energy. So you have a boost between the center of mass the hadronic center of mass rest frame and the partonic center of mass rest frame, and this boost is completely determined by the ratio of x1 and x2. Okay? So this means in particular that if you look at the leading order process, so the leading order process would be the process in which there are just 2 partons that hit each other and produce a WZ without radiating, without anything else in the cross-section here. So the cross-section here would just be quark, anti-quark W. Then the invariant mass is completely determined by how much energy the 2 partons are bringing in. And the boost is completely determined by whether x1 is bigger than x2 or x2 bigger than x1. So if you go and look at the leading order cross-section for the rapidity distribution, you discover that it's just the parton luminosity with fixed x1 and x2. Okay, so at leading order, W or Z production fully measures the momentum fraction of the 2 partons that are coming in the collision. So this is very important if you want to access PDF. Now, of course, at higher orders, that's no longer the case, but at leading order, this gives you a direct handle on the kinematics of the 2 PDF. So this was the rapidity distribution. The other thing that you can look at is the transverse momentum distribution. So instead of integrating over PT and looking at the boost, you integrate over the boost and you look at the transverse momentum. Now, the nice thing here is that you can prove rigorously that the longitudinal kinematics and the transverse kinematics completely decouple. So that means that if you calculate the hadronic cross-section for a fixed value of PT squared, that's given by a convolution of 2 PDFs, which are longitudinal, they depend only on the longitudinal momentum fraction, times a partonic cross-section, which depends on a transverse momentum, which is the same transverse momentum which you got here. So this means factorization applies at fixed PT. There is, however, a glitch, which is the following, which is that, of course, if you're producing a guy like this with fixed transfer momentum, you need more energy. The minimum energy that you need is not just the one that you need to produce the guy with given invariant mass. You need also some energy that you have to spend to give it some transfer momentum. So the minimum energy that you need in order to produce, say, a W with a certain value of PT is actually, well, you see it here. I'm sorry, there is a minus here. There should be, God, I screwed up. There should be a plus sign here. So the minimum energy that you need is m squared plus pt squared here. Yeah, here it's written in the picture is wrong, but in the slide it's written correctly. So the minimum energy of the center of mass, partonic center of mass collision is the invariant mass, but there is also a bit which you need in order to produce the given p. Okay, now this means that the lowest limit of integration over the momentum fraction is now higher than the one that you'd have to do a fully inclusive cross-section, because you need also something to produce this PT. And this then screws up this factorization of longitudinal and transverse kinematic, because you get that the lower extremes of the longitudinal momentum integration depends on the transverse momentum integration. So you screwed up this factorization, but you can fix this by changing scale and by picking as a scale not the invariant mass of this guy, but rather the minimum energy of the final state. So this S min here. If you do that, then you have a new scaling variable, which is the ratio of this new scale divided by the center of mass energy, and then you're back to the convolution. So this is a nice example of something that you may have heard of, maybe also in George's lectures, namely that when you actually look at the factorization formula, typically you look at fully inclusive things where everything is easy and you've got Q square, which is invariant mass, and your Kn(x), and everything is obvious. But the actual scale for which factorization works is something that, if you're looking at a more complicated process, should be decided by actually looking typically at the kinematics of the process. So, if you were doing top PT bar production, it would be even more complicated. So what is or if you're doing jet production, there has been a long controversy. What's the right scale for producing a jet? I'm not going to get into that, but that's something that you can only figure out once you sit down, you do the kinematics, you calculate the diagrams, and then you realize what is the choice of scale such that longitudinal and transverse kinematics factorize, because that's what factorization is all about, factorizing the longitudinal kinematics from any other degree of freedom which you may have in the collision. And this is the simplest example I could think of factorizing transverse and longitudinal purely based on kinematic consideration. Okay, so factorization is nice, but it obviously raises the immediate question. If I'm looking at something, so let me go back. If I'm looking at something like this or something like this, and I measure it. I measure in an actual experiment the cross-section with fixed y and m square, or with fixed m square and pt square. What is this telling me about the PDF? So what is the value of x that I'm measuring? Now, in this case, that's easy because at leading order, you're fixing x1 and x2. But for example, already for transfer momentum, it's not so easy because you have an integral with this new weird variable. And you like to look, okay, if I measure the cross-section in an actual experiment with fixed PT, which PDFs are giving the dominant contribution? Now, this is not so easy because you've got the convolution. And the convolution is complicated because, for example, when you fix the physical tau, which here is this weird tau prime, then the PDF actually depends on the luminosity in this case, depends on the ratio of tau prime over x integrated over x. So, if you take a large value of tau prime, actually the PDF may be contributing at the lower limit of integration where it's actually the smallest value of x and converge. Now, the way to solve this conundrum is to use Mellin transfer. This is something that I'm told George briefly talked about in yesterday's lecture. Some of you will probably know everything about Mellin transforms, but let me spend some time on this because I think this is useful and instructive. So Mellin transform, it's just a mathematical construct, which is a close relation to the Laplace transform. So if you have some function of x here, I'm thinking, say, the PDS, which depends on x, and x varies between 0 and 1 because it's a momentum fraction. The Mellin transform is the nth moment, meaning the integral of the function with a weight x to the n. And for a reason which I'll tell you in a second, one calls the moment actually n. So it's shifted by 1. So the first moment is when you integrate with weight x to the 0, so with no weight. So the integral of the function is called the first moment. And the reason why you do this is that if you change variables from x to log 1 over x, so if you change variable from x to log, then you get rid of this -1 because it goes into the Jacobian, and you get a Laplace transform. And everybody knows about Laplace transforms because they are like Fourier transform with an extra I. Okay, so once you realize that the Mellin transform can be inverted like Laplace transform by changing variables, which means you integrate over n in the complex plane of n along a line which is parallel to imaginary axis, and I'm going to get to this in a second. So notice that the Mellin transform transforms a function of real x, so x between 0 and 1, so with a real compact domain, onto a function of n complex, where n lives in the whole complex plane. So this may seem like a disadvantage, but it's actually a big advantage because, I'm sure you know from your mathematical methods course that analytic functions in the complex plane have a lot of nice properties, which typically functions on the real axis on a small interval don't have. So it's much more useful to look at the Mellin transform if you want to understand the analytic properties of a cross-section or of a Parton distribution, because then you can use the powerful machinery of complex analysis. The property of the Mellin transform, which is most useful to us in the context of factorization, however, is that the Mellin transform transforms a convolution, which is what we've been having for the previous 10 slides, into an ordinary product. So if you have a convolution of two functions, f and g, take the Mellin, that's just the product of the two Mellins, okay? So it undoes the convolution. So this means that our factorized expressions that I was showing in the previous slides become trivial. So for example, for lepton-hadron, a structure function now is just a sum over Parton species of Mellin transform of the corresponding PDF times the Mellin transform of the corresponding Partonic cross-section, which is usually called C in lepton-hadron, but it's just the Partonic cross-section. So it's the same thing. Historically, it's called C. And hadron-hadron, likewise, you have that the physical sigma factorizes into a sum over all possible pairs of incoming partons of Mellin transforms of Partonic cross-sections times luminosities, and the luminosity in turn is just the product of the two PDFs. So Lij Mellin is Fin Fjn. And you see the nice thing that has happened, that in the convolution, you have that the argument of f and the argument of g are not the same. One is x and the other is x over y, while here the argument has become n everywhere. So you're evaluating everything at the same n value. And this proves very important to answer the question which I was asking, which is how do you relate the kinematics of something that you measure in an experiment to the underlying Partonic kinematics. If you measure at one value of Q square and PT square, which PDFs are giving the basic contribution? So the way to answer the question is to look at the inversion formula here. So the inversion formula, I was saying, is like an integral on the complex n plane that goes from minus I infinity to plus I infinity. So it's parallel to the imaginary axis. And it turns out that if you think about it, so either you remember from your mathematical methods or calculus that the Laplace transform has a convergence abscissa, or you work it out here. So this means that there will be some value of the real part of n such that all the singularities are to the left of it. That's called the convergence abscissa. To the right, everything is finite, and you can see it if you look at the Mellin transform here. Obviously, if n is very large, because x is between 0 and 1, this thing is damping everything. And if you change variable, it's obvious because then you have exponential of minus n times log x. And then, this damps everything if n is very large. Okay. So this means that you have singularities somewhere to the left. In fact, if you remember the qualitative plot that I was showing here, you can see in this plot that the integral, so the area under any of these curves is the integral of the PDF, because it's log scale, but it's x times the PDF. So that means that the integral of a C PDF or the gluon is infinite. You have an infinite number of C plots, right? Because this goes all the way to the infinity in log scale, and this is not going to zero, okay? So this means that the first moment of a C PDF diverges. So this means that if we look at the Mellin inversion here, you must have a singularity at n equal 1. Now, I've drawn this as a simple pole because I know it's a simple pole, but it doesn't matter. The really important thing is that you have a divergence here. So the convergence abscissa is to the right of 1, because the first moment of the C diverges because you have an infinite number of C points. Okay, so you're integrating to the right of this convergence abscissa. So when you do this integral, this inversion integral, it turns out that it's most efficient to do this integral by a saddle or stationary point or semi-classical approximation, I don't know how you call it. And let me remind you, so I'm sorry to go into this slightly technical detail, but it's important. So you're doing this integral over this contour here. And of course, you can move the contour to the left or to the right. As long as you don't hit the singularity, the integral is all the same. You can deform it. You can go like this, whatever. It doesn't really matter. You just should keep it to the right. And it turns out that you can pick the ideal point to do this integral by looking at a stationary point of the integrand, so the function which here I call big sigma of n. Big sigma of n, remember, is the factorized expression, partonic time luminosity, which in n space is just a product. So you go and look at this guy by doing the following. You take the integrand, so integral dn of something, and you write this integrand as exponential of something. Okay, you can always do that. You can always write a function as the exponential of its log, okay? And then you look at the stationary point of this guy along the real axis. Now, this stationary point will always be a saddle point because, well, if you study complex analysis, you know that complex functions cannot, analytic functions cannot have an absolute minimum in the complex plane. So if it's a minimum along the real axis, it's a maximum along the imaginary axis. So you see the idea here, you're integrating like this. So if you have a minimum along the real axis, then you have a maximum along the imaginary axis. So you have this function is dropping very fast. And then it's very dominated by what happened at the point here. So you look for the point where this is minimum along real, and then you integrate along imaginary where it drops. And in fact, it's a Gaussian integral, which you can do exactly, and it's dominated by the value at the peak. Okay, that's the idea of the stationary point. So the idea is that the integral is incredibly dominated by the value of n, where you have the stationary point, which is along the real axis, which I'm calling n naught here. So it's a value where the integrand, which here I wrote like the log of this guy here, so minus n log x plus log sigma, is stationary. Okay, so then you look at what, how this guy looks like. So you realize, first of all, that partonic cross section at leading order is a constant. So that does not count very much. It varies slowly. The PDF, so the PDF we said is something that diverges at small n, right? At n equals 0, it diverges. If n is even smaller than 0, it diverges even more. So it's something such that, something that goes like x to the some power, which will be, what I wrote it like 1 minus k. And if you write it as 1 minus k, then the Mellin is 1 over n minus k. So the PDF looks like this. It's something that drops as n increases, okay? While the prefactor, the Mellin kernel, x to the minus n, it's something that on the real axis grows. Why does it grow? Well, because this is an inverse transform. You remember, in the direct transform, we had x to the plus n, which drops. But in the inverse, we have x to the minus n, which now grows, okay? So this grows. So you get this, you always get a saddle somewhere by the interplay of the PDF that drops and the kernel that grows. And that this gives you some value here where you have the minimum. And then the hadronic cross-section, which is the inverse Mellin, because, what you measure in an experiment lives in X space. So it's inverse Mellin of what you got in n space. But this can be written as the saddle point integral in n space. So the hadronic cross-section is effectively the product of the partonic cross-section, PDF1, PDF2, all evaluated at the saddle point and naught. And the saddle point and naught is the solution of this equation, which is completely fixed by the hadronic kinematics. So this means that given the hadronic kinematics, you work out the saddle, and the saddle is telling you which is the n naught value of the Mellin transform at which you're evaluating the PDF and the partonic cross-section. So this gives you an exact map between hadronic and partonic kinematics, except that the partonic kinematics is in Mellin space. You must do the exercise of doing the Mellin, but fine. Then you know that if you have a given value of x or tau, that corresponds to a given value of n. So then let's look at how this works qualitatively. So let's say you're looking at smaller x. If you're looking at smaller x, log 1 over x is bigger, so this guy grows faster. So smaller x, this guy grows faster, which means that the saddle, which is the interplay between these two things, is moving to the left, right? Because this guy is growing faster and faster, so this moves to the left. So this means that at small physical x, both sigma hat and the PDF are evaluated at small n. And this is what you hear sometimes that, say you're interested in resummation, then small x means you look at the log at small n, or you're doing soft resummation, Sudakov resummation. That's the opposite. That means that x is large, is closer to threshold, and then you look at the large n contribution, and indeed Sudakov resummation resums logs of n, which are important when n is large. So the saddle is telling you why small x or large x correspond to small n and large n at the partonic level. Okay? Now, let's actually look at what happens when you evaluate the saddle point with given PDFs. Okay? So an obvious observation is that the C and the gluon grow faster than the valence, right? I mean, a small x, they go up faster. Okay? That means that the C and the gluon have a singularity which is more to the right in the n plane. Okay? So if I look at the position of the singularity here, this will be 1 for the C, but it would actually be 0 for the valence, because the valence is integrable. You remember, number of valence quarks is fixed. So I have no valence singularity at 1. So the singularity in the C is to the right. The singularity of the valence is more to the left. Okay? Very good. Now, if the singularity is to the right, that means that the saddle moves to larger n. Okay? So if you look at the process which is C dominated, the n value will be larger, the n saddle value will be larger. If you're looking at the valence dominated, the n value will be smaller. Now, this has a very simple physical interpretation, which you sometimes hear. So you hear people saying, well, the gluon, for example, you say people here saying, Higgs production is threshold dominated. And you say, hang on, what do you mean threshold dominated? The Higgs mass is 100 GeV. The center of mass energy of the LHC is 13 TeV. How can it be threshold dominated? You're very far from threshold. But then people tell you, yeah, but the Higgs production happens through gluon fusion. And gluon are C. The gluon carries a small fraction of the proton, of the parent proton's momentum. So the gluon is very peaked at small x. So the center of mass energy of the protonic collision is predominantly not 13 TeV, it's much less, because the two incoming gluons will carry a tenth or 100th of the energy of their parent proton. So instead of being 13 TeV is 1 TeV, they carry each 1 over a third, or even 100, so it's 100 GeV, which is the Higgs mass. So this is why Higgs production is on threshold. And you see that this is what the saddle point of argument is telling you, because if the gluon is more peaked at small x, then n singularity moves to the right. And if n saddle moves to the right, that means that you're evaluating both the PDF and the partonic cross-section at large n, but remember, large n is close to threshold. So this is consistent with this. So this simple naive physical interpretation works because it's the saddle point argument. And I illustrate this here with these two plots. So here I'm showing the position of the saddle for Drell-Yan production for a pure C, C valence, and pure valence. So pure C is red, C valence is blue, and pure valence is green. And you see that indeed the saddle is moving to a larger n value. The saddle is here. So if I'm looking at tau equal 0.01, then the saddle is like 1.5 for valence, 2 for C valence, and I don't know, 2.5 for pure C. Now, what does valence, C valence, and pure C mean? Okay, so for example, let's say you do W production at the tevatron. Tevatron is PT bar. So you pick the quark from the proton, the anti-quark from the antiproton, you pick two valence quarks, and it's a pure valence process. Okay, then let's say you do Higgs production at the LHC, it's gluon, it's CC. If you do W production at the LHC, it's proton. So you pick the valence quark from the proton, but then you must pick an anti-quark from the other proton. So it's valence C, because one of the two has to be an anti-quark. Okay, and then you see the three cases. And indeed, if you go and look at the saddle for Higgs production at the LHC or Drell-Yan production at the LHC, again, you see that, say, tau equal 0.01, the saddle for Higgs is 3, tau equal 0.01, the saddle for Z production is 2 point something, because this is CC and this is C valence. Okay, so this tells you which value of the kinematics you're exploring in different processes, and it puts on the firm footing this kind of naive physics intuition that the guy that is peaked at small x carries a small momentum fraction, and therefore the partonic process is at much lower energy. Okay, so this is the end of my factorization and kinematics, and I leave the summary slide here because it's just a repetition. This is just a way of summarizing what I said. And I'd like to spend my last 10 minutes looking into a little more detail at the qualitative features of PDFs. Okay, so I already said that I'm plotting XF versus log X, that the gluon was divided by 10. And here I have two plots because I'm showing the PDFs at two scales, at the lower scale, 5 GeV, and the higher scale, 500 GeV. And if you compare, I mean, so the extra information in comparison to what I had before is the scale dependence. And when you compare the two plots, you see that the features which I mentioned, namely the rise of the C, the bump in the valence, become stronger at higher scale. So, well, look, the scale is the same, but you can see that the rise of the C is much more pronounced at high scale. So when you move to high scale, everything shoots up in the C, while the valence, you see that the bump becomes a bit lower, even though the integral must be the same, as I'm going to emphasize in a second, and it moves a little bit to the peak moves a little bit to the left, okay? So you get a depletion of the valence at large X when you move to higher scale. So what I'm going to show in the last 10 minutes, I think I'll go 5 minutes over time, contrary to what they said. And what I'm showing in the last 10 minutes is that you can explain all these features purely on the basis of perturbative considerations. So the first important consideration is sum rules. There are things that must be conserved. So the baryon number is conserved. That means that the integral of the up minus anti-up quark distribution had better be 2 at all scales. And that had better be twice the number of down minus anti-down in the proton. Of course, in the neutron, it would be reversed, okay? So, 2 valence up and 1 valence down. And of course, the strangest charm, the beauty, and top, they must all be 0. If you integrate them, you have the same, quark. The proton does not carry strange as one. So the total number of strange quarks and anti-quark must be 0. So that's the first thing. Second thing is momentum must be conserved. That means that if you integrate, now not just the PDF, but the PDF times X, so you have the mean value of the momentum carried by the sum of everything. So 2NF plus 1 PDFs, up, anti-up, down, anti-down, dot line, to the top, anti-top, plus gluon, it must add to 1. It will reshuffle at different scales, but the sum total must be 1 at all scales. Okay, so first of all, this explains the valence bump. So this is a nice exercise that was done by a former graduate student of mine who tried to do a PDF fit from DIS by generating random data. So he generated random structure function data, completely random, and then fitted them using a Gaussian process. A Gaussian process is a mathematical way of doing a fit, which is completely independent of the particular details of the function you're fitting. I can tell you more about it if you wish. And he just imposed two things. He imposed that the PDFs vanish at x equal 1, and he imposed that the sum rules be respected. And then these are the valence PDFs he got from the fit. So this is like saying, if you have a valence bump, that's nothing to do with detailed physics information. It's just telling you some rules and that the thing must vanish at s equal. Okay, so that's and then of course you get the some fluctuation because the data are random. But there is no information in this data. The information is in the prior, if you wish, in having imposed the sum. So the valence bump comes from the sum rule. Okay. Then the other ingredient is evolution equations. Here I have to spend a few minutes. So you heard from George that PDFs satisfy evolution equations, and the evolution equations, the DGLAP or Altarelli-Parisi equation, are especially simple in Mellin n space because they become decoupled ordinary differential equations. Okay, so each PDF evolves with an anomalous dimension, which is the Mellin transform of the splitting function, and you just have they are differential equations with respect to log of the scale, which I'm calling t here, and then you have that there is one combination, which is the sum of all quarks and antiquarks, which satisfies a 2x2 evolution equation together with the gluon. So the sum over all the quarks and antiquarks mixes with the gluon. And then the remaining 2nf minus 1, you have, 2nf plus 1, you have 2nf quarks, up, anti-up, down, anti-down, plus the gluon. So 2nf plus 1 PDFs to satisfy this equation. The remaining 2nf minus 1 satisfy decoupled equation, and you can pick any linear combination you want of the remaining ones. So you can pick any differences, they will always satisfy decoupled equations. So how many independent anomalous dimensions do we got? This is very important. I mean, it's a triviality, but it's very important. So at leading order, there is just one QQ. So we have these four, and then we have one QQ that drives the evolution of any difference. So if you take up minus anti-strange, it evolves with the same gamma QQ as top minus anti-bottom or whatever, or up minus strange or whatever. Any difference will evolve with the same gamma QQ at leading order. So you have four animals. However, next to leading order, you already discover that, first of all, the QQ in the 2x2 matrix is different from the QQ in the decoupled equation. So you already have 5. You have the 4 matrix elements here, and you have a separate QQ for the difference. And moreover, this difference anomalous dimension is different according to whether you're looking at a Q minus Q bar combination or a Q plus Q bar combination. So let's say if you take up minus strange or up plus strange, they will evolve with different combinations with different anomalous dimensions. So at this point, you have 6. And then if you go at next to leading order, you have 7 independent anomalous dimensions, because then you have that the Q minus Q bar combination has 2 different anomalous dimensions according to whether it's the same flavor or a different flavor. So up minus up bar evolves with a different anomalous dimension as up minus down bar, which in turn evolve with a different combination as up plus up bar minus down plus down. Okay, so which PDF combinations evolve independently? At leading order, you have the gluon, the singlet, and any NF minus 1 combination of the other ones. And next to leading order, we have the gluon, the singlet, and any linear combination of Q minus Q bar, and any NF minus 1 linear combination of Q plus Q bar, and F minus 1, because the sum of all of them was already mixing with the gluon. And next to next, you have a total singlet, which is the sum of all quarks and antiquarks, a total valence, which is the difference, so the sum of all quarks minus the sum of all antiquarks. The first one mixes with the gluon, the second one evolves independently, and then you have an F minus 1 linear combination of Q minus Q bar and Q plus Q bars. And there is an customary iterative way of constructing them, which is to start with gluon, singlet, and total valence, which is, so total valence is the sum of all quarks minus the sum of all antiquarks. And then you construct iterative Q plus Q bar and Q minus Q bar non-singlet combination. So for example, let's say you only have up and down. Okay, so if you only have up and down, you have the total singlet is up plus a bar, down, down, down. Total valence is up minus a bar, down minus down bar. And then you have the triplet, which would be up plus a bar minus down bar, and up minus a bar minus down minus. Okay, so you have the two iso-triplet combinations with the plus Q bar and minus Q bar. Then if you go to three flavors, you construct what is called the octet. The numbers refer to SUN representation, but it doesn't matter. It's really historic, which would be, so you start, let's say you have up, down, strange, charm. Okay, so you start up minus down, up plus down minus 2 strange, up plus down plus strange minus 3 charm, and you keep going like this, and you get all the combinations. And you have them with plus or with a minus, and that gives you the two different counts. Okay, so, trivial piece of information, but that explains everything when you look at the qualitative features of the anomalous dimension. So the qualitative, so here I'm showing the anomalous dimension, QQ, QG, GQ, GG at leading order, but the higher orders reproduce this. So first observation, the gluon sector has a singularity to the right, okay, at n equal 1, while the quark sector has a singularity at n equals 0. Now remember that because you evolve, the singularity in the anomalous dimension will produce a singularity in the evolved result. So whatever you stick in, the gluon is going to get a singularity at n equal 1 because it comes from the anomalous dimension. So we start understanding why the quark, the gluon and singlet, and moreover, since the gluon mixes with the singlet, also the singlet will acquire. So we start understanding why the C and the gluon have the singularity at n equal 1. Whatever you stick in at the non-perturbative level, as soon as you turn on perturbative evolution, this n equal 1 singularity spills over in the evolution. Okay. Then you notice that gamma QQ vanishes at n equal 1. Now this means that the difference Q minus Q bar is conserved, which is baryon number conservation. The fact that the total number of up minus anti-up, down minus anti-down, strange minus anti-strange cannot depend on scale. That's fixed. That comes from the vanishing of this guy here. And then because this guy vanishes here, it must be negative on one side and positive on the other side. And it's negative at large X and positive, negative at large X, positive at small x. And this you understand. So the diagonal ones, QQ and GG, you understand, because what the anomalous dimension is telling you is what happens when you have a quark, QQ, or a gluon that shed gluons. Okay, so if a guy is emitting, so you have a quark and it's emitting gluons, its momentum fraction will decrease, right? Because it's emitting stuff. So at large n, which is the large x component, remember large n, large x, the anomalous dimension is negative because he's emitting stuff. So it's less likely that you carry more momentum. And it's more likely that you carry less momentum fraction. So this is why this guy is positive at small n and negative at large n, and likewise for this guy. And if you wish, this again follows from momentum conservation because the sum of all these must add in such a way that momentum is conserved. So, the fact that the momentum fraction of something that is emitting gluons decreases at large n and increases at small n follows from momentum conservation. Okay, and now we can explain all the qualitative features, and this is basically my last slide. So the valence bump is explained by some rules, like I told you, even with random data. The fact that small x gluon grows, and it grows a lot, you remember the scale is G divided by 10, because the gluon has a singularity to the right of all the other guys. So it's growing like hell, okay? But then it also mixes with the singlet. So eventually also all the singlet is the sum of all. So they all mix with the gluon, and they also acquire small x rise eventually, which is less strong than that of the gluon, but everything is rising at small x. So all the individual Q bar combination is rising. Is when you take a difference that you see the bump. Okay? And the sign change of the anomalous dimension is the reason why the growth of the C is much stronger at large scale, which you see here, and the peak is lower and moving to the left at high scale, because you see this phenomenon of momentum being, the momentum fraction moving to smaller momenta because you have radiation as a consequence of the qualitative shape of the anomalous dimension. So you understand completely this. And then there is one thing which, last thing I'd like to mention, which is the peculiar fact that, as I mentioned, the non-singlet QQ So, the anomalous dimension of the Q minus Q bar combination is different or according to whether I and J are the same or different, means that if you take any individual combination, like say strange minus anti-strange, it does not evolve multiplicatively if you go next to next leading order. It has two different anomalous dimensions, which means because it does not evolve multiplicatively, it's a linear combination of two guys that evolve at different rates. So that means that if it's zero at some scale, it will not be zero at other scales because it's not just a factor times what it is. It's a linear combination of two guys that evolve independently. So this means that any combination of even heavy quarks, I mean, the total number will be the same, but they will be different at high scale. So if you look at, say, the charm and anti-charm, or even the bottom, anti-bottom PDFs of the proton, the total number of bottom and anti-bottom is the shape, say. But the shape of the B and B bar distribution will not be the same, because even if they were the same at one scale, evolution would drive them to be different. Of course, it's a small difference because it only starts at next to next order, so it's an order alpha square effect. But if you go and look, you'll find that strangely, the proton carries a different shape of B and B bar quarks, or T and T bar quarks. And this brings me to the end. Again, this is a summary, which I'm not going to read through because it's just a summary of what I said. And I conclude with a bunch of questions which you may want to consider for the discussion session tonight or the next week. So, our PDF probability, they are positive. What we discussed, they are not positive, but if not, why not? That's the interesting question. And do you understand why the number of anomalous dimensions increases with perturbative order? Could you draw the Feynman diagrams? It has to do with some Feynman diagrams that contribute to the anomalous dimension. So, for example, why is QQ for singlet and non-singlet the same at leading order and not the next leading order? Why do some rules hold at all scales? There's a basic QFT reason, but maybe you can think about it. And can you explain it in anomalous dimensions? And you expect PDFs to, of course, x greater than 1, the PDF must be 0 because everything must be 0 because it's above threshold. You cannot produce something for which you violate energy conservation. But do they have to vanish when x equals 1? I mean, maybe they could go to some fixed value and then have a jump. And if so, why? So these are my questions for discussion. I'm sorry that there were no questions during my talk, but maybe there are a few questions now.
Yes.
Yes.
Probably I missed, but 2 slides before, you mentioned that it's impossible to cancel the Q and Q bar to all scales.
Yes.
But does that mean at NLO the sum rule is broken?
No, not the sum rule. So the point, I mean,
after you integrate it,
yeah. So the point is, of course, here they will all vanish. But as soon as you move to the right or to the left, then you have that gamma QQ of the up minus. So gamma QQ of the total valence will be different from gamma QQ of the triplet valence. So maybe I should write it. So the point is that if you take up minus up bar plus down minus down bar, and up minus up bar minus down bar, these two guys have two different anomalous dimensions. Okay, so in particular, if you take this plus S minus S bar, okay, and then you take up minus a bar plus down bar minus 2S minus S bar. Okay, these two guys have two different anomalous dimensions at next to next. Okay, this means that S, so this you call V and this you call V8. Okay, this means that if you want to write S minus N star, this is a linear combination of V and V8. Okay, with the appropriate factors. So it's like C1 plus V plus C2 V8. Okay, and these guys depend on scale in a different way. So if you do S minus S bar at the Q square, this will be, alpha of Q square divided by alpha of Q naught square times gamma valence times C1 V of Q naught squared plus same, I guess gamma valence divided by beta naught. And this is gamma 8 divided by beta naught, same alpha ratio times C2 of V8 of Q naught square. So if you picked the factors C1 and C2 in such a way that this was zero at the starting scale, because they depend on scale in a different way, this will develop, yeah. On the other hand, if you integrate both sides, if you take the integral, then then the integral of this will evolve with a gamma v for n equal 0, and then n equals 0, and these will then satisfy some rules that this does not exist. Okay. And this will then be equal to s minus s integrated at q naught square. So the first moment will not evolve and it will remain 0, but the shape will be distorted. Okay. And by the way, the fact that s minus s bar is not 0, for example, it's not 0 at large x, was discovered experimentalist. Fred is smiling because when it was discovered, it was surprised. And then I think it was Stefano Catani who pointed out, look, I mean, you shouldn't be surprised. You just have to look at the anomalous dimension and then it's obvious. And he pointed that out, I don't know, 1995 or something like that when it was discovered. And you know, more recently, there is some evidence that maybe even the charm PDF has this kind of symmetry. Of course, you know, it being a next leading order. So, of course, in the case of the strange PDF, there is no reason why the non-perturbative strange PDF should be have the same shape for S and S bar in the first place. Okay. In the case of the charm PDF, if you think that the dominant contribution to the charm PDF is the charm is radiated by the gluon in pairs, then you expect that the starting PDF should have the same shape. And in fact, if you impose matching conditions, they do have the same shape, but they have the same shape again, up to some fixed order. If you go to next cube leading order, you start getting. So it's a small effect, but it's there.
Yeah, we have time for the questions. So Josh?
Yeah, a quick question. With the valence contributions as well, I've seen sometimes that between proton or baryons and mesons, there's a plus minus sign difference between the two. Because sometimes PDFs are plotted from -1 to 1, where the negative X region is the negative of the anti-quark.
Yeah, so right. I mean, if you get the PDFs, or I mean the whole factorization from the OPE, the negative X region corresponds to charge conjugation, so to interchanging quark with anti. So what you're asking is whether there is a symmetry that relates the QQ and QQ bar anomalous dimensions. If I understand correctly, or maybe I misunderstood the question.
Yes, for mesons though, because with baryons, sometimes there's it's U minus U bar or U plus U bar.
Right. Yeah. So this is really actually this is. So first of all, the anomalous dimensions obviously are a property of they are perturbative objects, so they are a property of the Wilson coefficient. So they don't depend on whether you're looking at mesons or baryons, right? So the scale dependence is completely universal and nothing to do with the boundary conditions that you stick in. So then the relation that you have, for example, between a gamma Q, so this is actually related to question number 2 that I was asking here. So the reason why this happens is that at next leading order, I mean, maybe this is something that should go in the discussion session, but you should start asking whether gamma QQ and gamma QQ bar are the same or something. Now, at leading order, you can only do this, obviously, okay? And this is gamma QQ leading. But the next leading order, you can also do this, okay? And then this is a contribution to gamma QQ at next leading order. Now, this means that at next leading order, this guy here could be, so this is gamma QQ, but you can also do this. And then this is gamma QQ bar, okay? And it turns out that actually gamma QQ and gamma QQ bar are not the same because of Pauli principle, because in one case, you end up having a QQ bar pair in the final state, while in this case, you have a QQ pair. Here you have this is a quark. Sorry, this is an sorry, this is a quark, and this is a quark because this is an anti-quark. So in this case, you have a quark pair in the final state, while in this case, you have a QQ bar pair. And it turns out that when you do this, because of the anti-symmetrization, these two guys are different. And this is, so I already answered the question, you explained this, but then this tells you that in the, in the case of mesons, for example, you're gonna have that the QQ and QQ, I mean, in principle, the wave function you start from is symmetric, but then you have to keep into account that the QQ and the QQ bar splitting are not symmetric.
Other questions? Yeah.
So is it always possible to write a sum rule in terms of a relation between the anomalous dimensions?
Yes.
Okay.
Yeah, this is, yeah, so, sorry, that was.
No, that was, I thought about my question and then.
Yeah, so, no, so the point is that, sorry?
You keep talking.
No, I mean, it's a good question. I mean, the reason why the answer is yes is that, what, going from Mellin space to physical or X or momentum space is just, if you wish, a mathematical operation. So you can decide to write your evolution equations in P space, in X space as already Paris equation with splitting function of the convolution, or then you take a transform and you just map these. So whether you write d by d log square of q of x, q square as integral dy xy p, say q of x over y, q y and q square, or d by d log q square of q of n q square equal gamma qq of n q n of q square and pqq and gamma qq in turn. So gamma qq, say, is written as gamma alpha of q square times gamma qq naught plus alpha square gamma qq 1. So the operation that takes you from this to this is a purely mathematical transformation. So you can always do that, and you decide which one you prefer according to I don't know, whether you prefer to solve a code in which you solve an integral differential equation by Runge-Kutta, or whether you prefer to take this, which is in principle trivial to solve, but then you have to invert by doing a complex integral in complex plane, which numerically is hard because it oscillates and it's a pain in the neck. But that's purely practical consideration. The sum rules are properties of ends. So so you can see that these are very good questions because they are answering the questions, or at least they are what I would consider good questions because they are answering the questions which I put on the slide. So the sum rules will then correspond to relations between gammas. So for example, the fact that the momentum sum rule holds at whole scales will mean that you have some linear combination of second moments, which does not depend on scale, okay? And that was, I think, written in a previous slide. Let me see whether I can get it, despite, maybe you have to click on to get rid of the Apple ID settings, thanks. Yeah, so you have a relation like this one here, gamma q, second moment of gamma qq plus second moment of gamma qg equals second moment of gamma gq plus second moment of gamma gg. And that, if you write the equation, you write the evolution equation for the sum rule, it was, I mean, the reason why I showed this on the slide rather than writing on the blackboard is that it would be a bit long, it would take me 5 minutes. But the way to do it is you go back to the momentum sum rule here, you write this sum rule here by writing d by dt of this guy here, which will be a sum of terms, and then you impose that when you set n equal 2 means second moment, which means the momentum integral, then the thing does not depend on scale, and this, then you see that it produces a pair of relations because you have two independent components of the vector, which correspond to these guys here. And if you then ask, so in this sense, it's more convenient to look at the sum rule in terms of anomalous dimensions, because then it's a simple linear relation between fixed moments. And there is a QFT reason for that, which is that again, I'm answering the question on my slide, but that's fine. The reason why you have the sum rule is that if you do factorization in deep inelastic scattering using the Wilson expansion, I don't know whether you're familiar with that, or then you realize that the moments of PDS, say, are matrix elements of operators, of twist two operators in the proton. So in particular, what you're looking at when you're writing the momentum rule is a matrix element in the proton of the energy momentum tensor. Okay, and then you just write the energy momentum tensor for QCD, which will have a bit which comes. So the energy momentum tensor for QCD will have a bit which is like psi bar gamma mu d nu psi, which comes from quarks, and then it will have something which is like f mu alpha f nu alpha, which comes from gluon. Okay, these are contributions to the energy momentum tensor. There are other terms because it must be traceless, so you have a subtraction. But these guys, twist two operators are operators where dimension minus spin is equal to 2. The energy momentum tensor is a rank 2 tensor, so it corresponds to it corresponds to spin equal 2, so it must have 2 free indices, and then which is why you have these 2 contributions, and then you have that the matrix elements of these 2 contributions are matrix elements of the energy momentum tensor. But the energy momentum tensor is a conserved operation, right? I mean, T mu nu is equal to 0. So you get ward identities from the fact that this is conserved that tell you that its matrix element cannot depend on scale. Okay, so that follows from the conservation. So you have these 2 implications. The first one is that the matrix element of this guy plus the matrix element of this guy in a particular combination are the second moments of the PDFs, and that the conservation law implies that that particular combination cannot depend on scale. So this is why you then have that this becomes a property of the anomalous dimensions QQ and QG, or GQ and GG evaluated. So that was a very good question.
Okay, let's thanks Stefano then. And a double thanks for his questions. Again, we'll have this session this evening, 7:30, to think about those, discuss those. We organized you in the first 2 days, but this day you're on your own, so we'll come back at 7:30. Relax, sort of just wander around, ask questions, but you can chew on these for a little bit. Quick announcements. We have some Tide Pods. They're very colorful, but they don't taste good, trust me. But there's a plastic bag, so get a Tide Pod and a plastic bag, so you can have clean socks for next week. And let's go ahead and break. We'll start at, I guess, about 10 of, sound good? So yeah, we'll break now and then we'll continue 10 of. Thank you. Thank you.